Hey everyone, this is our Limits and Derivatives unit. We're on video 8 and we're going to be talking about tangent line and velocity. So these are two different purposes for our first derivative. Alright, so the first example here is exactly what we did in class. So I'm going to do this with you just to give you a reminder. We were finding the slope of a tangent line that's to this curve. So we've got this x to the fourth minus 7x cubed plus 2x squared plus 15. And we're looking for a tangent line that occurs at exactly x equals -1. And we want to know the slope of that line. So to do this, the first step we did is we used the power rule and we found our first derivative to be 4x cubed minus 21x squared plus 4x. We know that the derivative of the constant is 0, so that's gone. And now we evaluate this at -1. So I have 4 times -1 cubed minus 21 times -1 squared plus 4 times -1. So as I calculate this, I get -4 minus 21 minus 4, or -29. This tells me that the slope is -29. So somewhere on this curve, this fourth degree polynomial, when it's graphed, at exactly x equals -1, the slope of the tangent line is -29. Go ahead and try number 2 now, or at least before you get to class tomorrow. Okay, examples numbers 3 through 6 are asking us to write an equation of a tangent line. So when I finish this, I should have something in the form of y equals mx plus b. Well, in order to do that, we're going to be using that point slope formula that I had mentioned. And so we need to know, first of all, the slope, and we need to know an ordered pair. So it looks like here I have an ordered pair, so we're going to use that, but I also need to find the slope. To find the slope, I'm going to use that x equals +1. From my ordered pair, I can see x equals 1. So just as we did in examples 1 and 2, we're going to first find our first derivative, which gives me 2x minus 4. I'm going to evaluate it at x equals 1. So at x equals 1, we get 2 times 1 minus 4, or -2. So I have a slope of -2, and I have the ordered pair that I'm going to use to write this equation. So I'm going to begin with my point slope. So it would be y minus a -1 equals -2 times x minus 1. I'll go ahead and simplify this and distribute that -2, and then subtract the 1 over to the other side. So it's -2x plus 1. So this is the equation of the line that is tangent to this parabola at exactly 1, -1. Okay, so number 4 is very similar. You can pause now and do it, or you can take a look at it later. Number 5. The first thing we're going to take care of here for number 5 is we have to, again, find the ordered pair. So in order to find the ordered pair, which was given nicely in number 3, but not so nicely in number 5, is I have to substitute this into the original. And that is because this x value is on the original curve. So I'm looking for this. So I'm going to substitute it in. 3 cubed minus 3 plus 4 is 27 minus 3 plus 4. And that's going to turn out to be 28. So the ordered pair I'm going to be using is 3, 28. Now we need to use the new process that we have, and that is to find the tangent, or the slope of the tangent line. So I've got the first derivative to be 3x squared minus 1. I'm going to substitute in the 3. So it appears that I'm actually using the 3, the value x equals 3, in two places. The first thing I did was I looked for the ordered pair on the original curve. The second is that I'm finding the slope at x equals 3. So I have 3 times 3 squared minus 1, which is 27 minus 1, or 26. So that's my slope. I've got my ordered pair, and we're going to write the equation of the line. Y minus 28 equals 26 times x minus 3. So I have y minus 28 equals 26x minus 78. I'm going to add 28, and I get y equals 26x minus 50. And this is the equation of the line that is tangent to this first equation at exactly x equals 3. So if you need to slow down, review any of these two processes here. They're very similar, except you have to find the ordered pair, 4 comma what, in order to write the actual equation of the line. When you substitute in that 4, to get the ordered pair, you go into the original. When you substitute into the 4 into the first derivative, you get the slope. Same value of x, two different outcomes. All right, let's keep going. For number 7 and 8, we're going to be graphing f of x, which is the original function, and we're going to be graphing the equation of the tangent line. So I'm going to have to find the equation of the tangent line, just like we just did on numbers 3 through 6. So the first thing we're going to do is we're going to find the ordered pair. So I'm going to have 2 parentheses 3 halves squared minus 3 times 3 halves minus 5. So 2 times 9 fourths minus 9 halves minus 5. This is actually going to turn out to be 9 halves minus 9 halves minus 5, which gives me an ordered pair of 3 halves comma negative 5. So this is the ordered pair I'm going to be using to write the equation of my tangent line. To find the slope of the tangent line, I have to take the first derivative, so I have f prime of x to equal 4x minus 3. I will substitute in the x value to find the slope. So I have 4 times 3 halves minus 3. For my slope to be 12 divided by 2 is 6. 6 minus 3 is 3. So my slope is 3. My ordered pair that I will use is 3 halves comma negative 5, and now I can write the equation of the tangent line. So this still is the process that we were using in the previous 4 examples. So y minus a negative 5 equals the slope times x minus 3 halves. We'll distribute, and I'll get 9 halves, and I'm going to subtract 5, and I will get y equals 3x minus, and it's going to be 19 halves, which is 9.5. So this is the equation of the tangent line. Now, the directions tell me to graph both of them. So I'm going to use the graphing calculator to help me, because I can put these into y equals and very quickly get some ordered pairs from my table of values. So if your table is still on auto or on ask, or you've got all those things, all the table is blank, go to second window and make sure you turn it back to auto, and that will automatically fill it. So go back to table set, which is second window, and make that auto. All right, so from my table of values, I get a whole bunch of numbers here, and I don't have to graph them all, but I should probably pick some that make sense for this parabola so I can see the entire shape. So I'm going to start over here with x equals negative 2, comma 9, negative 1, comma 0, 0, comma negative 5, and 1, comma negative 6. Now if I stop there, even though I already have a bunch of points, I really can't see that this is a parabola, and I know it should be a parabola because it's an x squared. So 2, comma negative 3, and 3, comma 4. So at least now I have a shape that this is a parabola, so I'll go ahead and connect all of those. Okay, I'm going to change ink color so you can see the fact that I'm going to go ahead now and draw the tangent line. So I'm drawing this one in red, and I'll put that into the y equals as well. So I've got 3x minus 9.5, and I can look at my table of values for that one. And they're not going to come up so pretty because I'm adding on a negative 9.5. So no matter what I'm using, I'm going to definitely be coming up with some values that aren't so pretty. But that's okay. So at 0, negative 9.5. So I know my intercept is negative 9, negative 9. How about right here? 9.5. That's my intercept. And then 1 comma negative 6.5. Okay. Now I know that it should be crossing at 1.5 comma -5. So 1.5 -5. Oh, it looks perfect there. So let me get one more point on just a little bit to the right of that intersection, and then I feel like we've pretty much covered what we need to. So how about 3, -0.5? So that's a very nice line, and I can see that it is the tangent line, and it is touching right here. All right, so make sure you try number 8 for that as well. Okay, so lastly, we've got it's just another application of what we can do with the first derivative. So I'm going to introduce this. It's kind of a physics example. We're talking about velocity. So in order to talk about velocity, we actually have to talk about the position function. So s of t is the position at a given time. So since if we have a parabola, we kind of consider this, it's going to look like this, and we're talking about the position over time. So maybe we're talking about the height of this as maybe something is being thrown, a projectile. So this is the height, and that was what this would be in. So to find the position at 1.6 seconds, we're merely plugging in the value that they give us. So I have -8, 1.6 squared, plus 12 times 1.6 plus 10. If I go ahead and substitute that in and calculate it, I'm finding the height of this projectile at 1.6 seconds after it's been released or kicked or dropped or thrown. So -8 parentheses 1.6 squared. Make sure you're using parentheses just in case. It's always safer to use them than to forget them. So this comes up to be that the position at 1.6 seconds equals 8.72, and let's go ahead and label it feet. It could be meters or miles, but we'll go with feet. Now, to find the velocity is the first derivative of the position function. So I may write it as s prime of t, which equals the same thing as just v of t. So here I need to first find that function by taking the first derivative and applying the power rule. -16t plus 12. Now I'm going to evaluate v of t. Oops, I should write v of 1.6 because that's what we're going to do. We're going to substitute in the same thing. So now I'm looking for the speed that occurs at that time. So what is the speed of this? So I will put in -16 parentheses 1.6 plus 12. And I get a speed of -13.6 feet per second. So my position, my height, and then this is the speed, the rate of change. Okay, number 11. At what time is the position equal to 0? To answer this question, I want to know, when is the height 0? So before I go ahead and do anything, I'm sticking with s of t. I don't want a first derivative because I'm talking about position. To do this, I'm going to make s of t equal 0. So I'm going to take the t squared minus 3t minus 4 and set this equal to 0 so I can find out when is this equal to 0. To do this, I might have to use the quadratic formula. I might have to factor. There's going to be lots of ways we can find this. So setting this equal to 0, I have t minus 4 and t plus 1. So I get the two answers that t equals 4 seconds when it equals 0 and t equals -1 second. Well, since we know we're talking about time, I'm going to get rid of that -1 and we're going to say that the height of this projectile is 0 at ground level at 4 seconds. All right, the second part says, well, what time is the velocity equal to 0? In other words, what time is the rate of change equal to 0, the speed? So to do this, I'm going to merely take the first derivative, s prime of t, which is the same as v of t, and then I'm going to evaluate it equal to 0. So I'm going to have 2t minus 3. If I set v of t equal to 0, I get 2t minus 3 equals 0, or 3 halves, or 1.5 seconds. This is saying that the speed is equal to 0, that there's no rate of change at exactly 3 half seconds, or 1.5 seconds. Alright, so I've given you quite a lot to look at. Just remember that numbers 1 through 8 are really going towards exactly the same thing. The back side of the worksheet here is another purpose. It's a physics application of exactly why we would need the first derivative. We're going to continue on this throughout the rest of the chapter. Please leave notes on Schoology if you have any questions.